we were discussing the electro-optics for isotropic medium, and we started discussing the electro-optic effect in gallium arsenide. In between, we took up a discussion on the basics of how the light can be amplitude modulated, phase modulated, and polarization modulation, the basic configuration required and how the modulation takes place. And we will be again continuing with the electro-optics of this isotropic medium, that is in particular this gallium arsenide crystal, and we will be discussing now that the longitudinal configuration, that is when you apply a voltage along the length of the crystal along which the light is propagating, then how it has to be configured for phase modulation and for amplitude modulation, then what will be the consequence of that in terms of the modulation by refringence, then half voltage. So, in the then after that we will consider this transverse configuration. In the transverse configuration we will see the retardation, phase retardation, and then the transverse modulation, how what is the half voltage required in that case to switch the modulator. So, let us recall that in the case of an isotropic medium like gallium arsenide, the new principal axis in the principal axis system, the refractive index Nx can be written in this form with the original refractive index N0 minus this quantity is a function of the applied electric field along z direction, and in the similar way the refractive index seen by the light for y polarized light will be this, and for Nz there is no change. And so, these are the set of new principal axis system refractive indices. Therefore, the birefringence that is seen by the x and y polarized light in the new principal axis system will be delta n x y, which is equal to the difference of these two quantities, that is equal to n cube r 41 is the electro-optic coefficient of gallium arsenide into E z, and then the phase retardation, phase delay, that is equal to k 0 L, the length of the crystal along which over which the light propagates and interacts with the crystal, that is k 0 L delta n x y, which is equal to this. And we are familiar with this quantity, and we will be again encountering back and forth with this kind of expression. So, we find that this phase retardation delta phi is proportional to the applied electric field. So, in terms of the voltage, this will be again this phase retardation is proportional to the applied voltage, because all other quantities remaining constant. K 0 involves the wavelength, free space wavelength, then N 0 the refractive index of the crystal in absence of any electric field, length is L is the length of interaction. Okay. So, now we will consider the longitudinal configuration with emphasis on the phase modulation and amplitude modulation. Then we will consider the transverse configuration, which is different from this, and we will see that how the performance of the crystal can be improved by choosing the geometrical considerations like the length and the width of the crystal, which will be involved in this case, and this will improve the performance of the modulator. So, in the longitudinal configuration, as we know, you have a length L and you apply the voltage along the length of the crystal, and the light beam is propagating through the crystal in the z direction. Whereas, in the transverse configuration, you apply the electric field, the voltage, that is across the modulator in the x or in the y direction, whereas the light is propagating along the z direction. The length of the crystal is L, we will assume, and the width of the crystal is d. Therefore, for longitudinal configuration, we will first take up the phase modulation. As we will remember that for phase modulation, we will have to launch the light to the crystal with its polarization axis, which will be along one of the new eigen axis, that is x dash or y dash, and light will be propagating along the z direction. So, under this configuration, so let us look at this configuration, that we will be launching light along x prime or y prime, these any of these directions, and light will be propagating along this direction, that is along z direction, which is z prime, because z and z prime are the same. Crystal undergoes a principal axis system, it undergoes a rotation about z. So, z and z prime remains the same. So, in this case the light must be polarized either in the x dash or y dash direction, as I have mentioned, because once you apply the voltage, the polarization axis x dash or y dash, I only require the change in the refractive index along any of these directions, which will modulate the change in the refractive index will modulate the light, and there will be no analyzer at the output. There will be one polarizer which will be to launch the light along the desired polarization axis, say x prime or y prime. Okay, so, this is the configuration. Light will be launched along x prime axis or y prime axis. No, this is your x dash, x prime axis, this is y prime. It could be launched, this is the input polarization, I have shown with this arrow, this is the input polarization, which is halfway through x and y axis of the old system without any field. So, this polarization now moves through the crystal, and because the electric field changes, so this refractive index seen by this polarized light will be modulated. As a result, the phase will be modulated. So, this polarized light which will be available here will be modulated with the applied voltage. The phase of this light will be modulated. So, let us see that once again this n x is represented by this, n y is represented by this, which are the signatures of the applied electric field, n z is 0. So, light is launched along x prime or y prime axis. Let us suppose that first we considered that light is launched along x dash axis. So, without field, the two components along x and y sees the refractive index, which is n x equal to n 0. But with the field, the two components along x and y, because when you launch light along this axis, there will be two components, one is along this, another will be along this, they are at 90 degree to each other, they are normal to each other, these are two orthogonal components, but both of them, this x and y polarized light will see the same refractive index in absence of any field. So, there is no birefringence, there is no phase delay, but there will be a phase which will be carried over because of the length of travel along the crystal. So, without field there is no birefringence, both the lights along x and y will see this n 0, and with the field, the two components of light along x and y will now become n 0 n y, because there is no light along n y. So, the component of you have injected light only along this axis. So, along y axis the birefringence along y axis you have n 0, whereas along x axis this is the new refractive index seen by the light, which has the component along the old x axis. So, this birefringence n y minus n x, these are the two refractive indices, the indices. So, the birefringence the new along the new coordinates, that is x prime and y prime. So, this will be seen by this one, hence the induced phase change will be k 0 L into delta n x y, but delta n x y this has this value. So, we just plug in this value here, which will give me the phase retardation, that is del phi, phase change with respect to as a function of this E z. So, as you change the value of E z, the phase will also change. So, it will be phase modulated by this E z, that is the applied voltage. Okay. So, this is the setup. You have an input polarization which is along the new principal axis system, let us say x dash. So, this x dash light, it undergoes a phase change, because the x dash light undergoes a change in the refractive index as a function of the electric field, and then the output light will be phase modulated, because the refractive index changes, therefore, the phase also changes. But this change in the phase is now proportional to E z, which is equal to V by L. So, in this case this L cancels. So, therefore, the half voltage, that is the voltage that is required to get a phase change of del phi equal to pi, that is equal to V pi equal to lambda by n cube r 41. So, this means that a phase change equal to, it can be a convention that phase change equal to 0, which is equal to 0, but phase change equal to pi, which is equal to 1. So, switching from 0 to 1 requires a phase change of pi, or from 1 to 0, depending on the convention, depending on the protocol of the modulator design. Then the phase shift pi corresponds to switching of the modulator from the state 0 to state 1. So, that requires a voltage V pi. So, this we find that with the applied electric field V by L, the modulator, the induced phase shift is del phi is equal to pi, that is the requirement for switching, and this is, you can see that it does not involve any L or any other quantity. It is only the the wavelength, the original refractive index, and the electro-optic coefficient. So, it does not involve any other thing. So, therefore, it is independent of the length L, and it is linearly proportional to the voltage, that is this switching is linearly proportional to the voltage, the phase change is proportional to the voltage. So, let us use the typical values for gallium arsenide. These are the quoted values. We have shown that R 41 is equal to this, and N 0 for gallium arsenide is 3.5, 3.4, 3.6, 3.5. Let us assume that this is 3.6, and if we use a wavelength of 0.9 micrometer, then the V pi value, that approximately it comes out to be 18 kilovolt, which is a very large voltage, and it requires a very careful setup to handle with 18 kilovolt of electrical voltage. Now, so in this case, this half voltage is about 18 kilovolt. So, we conclude that for switching of the modulator, you require a voltage which is of the order of some 18 kilovolt, and that is pretty high. And now, we will see that if we change the configuration intelligently, whether we can reduce this half voltage for switching this modulator. Indeed, for the amplitude modulation scheme, we will see that the half voltage required will be less, will be half of the half voltage that is required for the phase modulation. So, in this case, we consider this setup now. As we will remember that for amplitude modulation, you have to set the polarization halfway between the new principal axis system, that is x dash and y dash, halfway through. So, that the moment you apply the voltage, both the components along x dash and y dash will have equal excitation. So, the front polarizer will be aligned with x axis, and this x axis will give you 50% of x prime and 50% of y prime when the voltage will be applied. So, that is the philosophy, and then there will be an analyzer at the output of the crystal. So, now the light which will be decomposed into x prime and y prime axis, they will travel with two different velocities, because these two light lights will see different refractive indices because of the electro-optic effect, and there will be a birefringence between these two lights, and then this birefringence acting over the length will give you the phase retardation. And if you place an analyzer which is crossed with the input, then the light will be periodically modulated with the frequency of the input signal. So, light, this is the configuration, light is launched along the old x axis and it will be shared by the two orthogonal polarizations which are the new principal axis system of the crystal, and then it propagates, develops a phase delay, there is a cross polarizer, you get a modulated output. So, once again, so this is the same relation for the same crystal and under the same configuration of the voltage and light propagation. So, now without field, the two components along x and y, they will once again the same thing, we will see the same refractive index n 0 and there is no birefringence, but when you apply the field, the two components along x and y will see these new refractive indices. So, you can see that one is more, another is less, depending on the value of the magnitude of the coefficient, one is more, another is less. So, that develops a, because they will travel with two different phase velocities, because they will see two different refractive indices, and they will in turn develop a delay between these, and this delay will develop a phase difference between them. So, the birefringence here is n 0 cube r 41 E z, which is double in the case of, if we consider the phase modulation where there was a divide by 2 factor here. So, the induced phase change in this case you will have to multiply with k 0 and the length of the crystal. So, that this will be the induced change in the phase between the two orthogonal polarized light in the new principal axis system. As a result, you see that this birefringence is now proportional to the applied electric field, and we will see how it depends on the electric field. You can see that L and L this time also will cancel, because everything remains the same, only we had arranged the input polarization which is halfway between the x prime and y prime axis, and you have set an analyzer at the output which is crossed with the input. This is the only difference in the configuration, and as a result you get V pi which is equal to this, and you can see that it is reduced by a factor half, and consequently, so this is the setup for this. This is the setup for this. You have this polarization which is launched along this, which is halfway through x prime and y prime. Then they develop the delay between the two eigenpolarizations which are along x prime and y prime, and because they will see different refractive indices, and at the output of this modulator of this polarizer which is at crossed position with respect to the input, you will get a. So, the half voltage required is now equal to V pi, which is half of the half voltage that was required in the case of phase modulation. So, if we use the typical values, then we find for this gallium arsenide using the same numbers that we have used earlier, that is n 0 equal to 3.6, lambda equal to 0.9, find that V pi is of the order of 9 kilovolt, which is half the voltage that was required for the phase modulation. So, there has been some improvement when switching from this phase modulation to the amplitude modulation, and still this required voltage is very high of the order of kilovolt, 9 kilovolt, and then we will see if we can improve this design of the modulator, so that the voltage required is much less. So, with that background of this phase and amplitude modulation in the longitudinal configuration, let us now see that how this transverse configuration of gallium arsenide isotropic crystal works. So, for amplitude modulation, the requirement, you see the propagation along x and the voltage is applied along xy plane, that is along the body diagonal of this xy. So, I will show you how this polarization has to be launched. So, in the case of transverse modulation, electric field must be applied along a diagonal of xy, that is you have old coordinate system x and y. So, along this line you have to apply a voltage. So, we can represent this electric field as 110 direction. So, the electric field components along x and y will be 45 degree inclination. So, it will be E y under root 2 for both of them, which are equal amplitudes. So, that is equal excitation of the two polarization modes are needed to work with this transverse modulation of this electro-optic system using this gallium arsenide and isotropic material. So, let us now once again do this little bit of algebra and recall this ellipsoid, index ellipsoid, which is these are the incremental changes in the refractive indices, permittivity, impermeability. So, this equation is once again very familiar, and we know that these are the coefficients which are attached to this cross components, that is the x y, y z, z x. So, this is the after the field has been applied. So, this is the new refractive index system. So, we will have to use the appropriate electric field configuration to reduce it to the principal axis system. So, when you apply this electric field 110, that is this under E x, E y and under root 2 this thing, then we have this index ellipsoid. Let us look at this system. You have, there is no terms appearing here, there is no term appearing here and here. So, this all remains n 0 x square, n 0 1 by n 0 square y square, etcetera, but only you have this which is dependent on this coordinate, that is this z dependent coordinates, that is these two are now excited. So, you have y z and z x. Therefore, this I replace this E x by E by under root 2. So, you get this form of the equation. Now, we will use this matrix diagonalization method and to find out the new principal axis system. So, we will not do that algebra, but you can, because we have done several times. If you do this, you just find the eigenvalues of this matrix equation, then you can see that n x will be equal to this half of n 0 r 4 1. So, this E is because of E x root 2 under root 2 into E x, I have written as E, and here also this n y will be equal to E. So, they are correct and with the appropriate factor. So, because this is E x, we will have a root 2 if you have to represent this E in terms of E x and E y. So, so n z equal to n 0, hence the induced birefringence for this. So, after you do this matrix diagonalization of this system of this matrix equation to get the principal axis the refractive indices for the principal axis system under the electric field, then you get these new refractive indices, and the induced birefringence this time will be equal to this. Ignoring sign means whether you take n x minus n y or n y minus n x, it is the magnitude which is important, which gives you the birefringence. So, now E is again for this setup. So, the phase induced phase delay between these polarized light orthogonal polarization is now equal to this. You have to again multiply k 0 and L, that gives you these equations. So, in this setup we have electric field E is V by D. So, if you plug in that E equal to V by D, you can see that both L and D they exist in the expression for this phase delay. So, del phi is now proportional to L, is proportional to the length L, but it is inversely proportional to D. It is inversely proportional to D, and it is also proportional to linearly proportional to the voltage. So, you have three quantities to control the phase of the modulator. So, for half voltage delta phi, this requirement is equal to pi. So, let us use so this pi equal to twice pi by lambda n 0 cube r. So, this is once again half voltage is also proportional to this. So, this gives you a feature that by choosing the ratio L by D, you can actually reduce the number. So, this case this was about 9 kilovolt. Now, let us suppose if this D by L is equal to 1 by 9, then it reduces to 1 kilovolt. So, the half voltage V, which is required to switch the modulator, can be reduced by taking a small value of D by L. So, this factor is now extra freedom now this time to reduce the half voltage, and then this is the one which we discussed is about when the voltage is applied across the body diagonal of the x and y in the crystal. But let us suppose you apply a field which is which makes equal angles, equal inclination with E x, E y and E z, then what happens? That is the electric field is now applied along 1 direction. So, let us have a look at this problem and try to find out, and we can repeat the same problem using a field which is applied only along x axis. Then we can use this matrix diagonalization to get the principal refractive indices, and after having this principal refractive indices, we can calculate the birefringence, and that is the same protocol, same rule that will have to be followed for all modulators. Then the birefringence, from the birefringence we can calculate the phase delay, and from the phase delay then we can calculate the half voltage, that is how much voltage is required to get a phase delay of pi, so that the modulator is can be switched from state 1 to state 0 or state 0 to state 1. So, that we can also calculate for the case of E x. So, these are the situations that can give a more insight and understanding about the various configurations that can be used for the crystal, for this electro-optic crystal, and to compare which configuration is more useful, which configuration will give you a lesser will require a lesser half voltage that can be found out. So, the summary of this discussion is that we started with the electro-optics of isotropic media, and then we were discussing this the basic configurations, how the crystal has to be configured with respect to the propagating light and the applied voltage, so that it can be used as a longitudinal modulation, phase modulation, and in the transverse configuration also how it can be used for amplitude modulation. In the present discussion, we worked out that how this, what will be the requirement for the configuration in terms of the input polarization, output polarization, the analyzers, and then what is the magnitude of the half voltage required for switching the modulator. We did the same thing in the case of transverse configuration, and we found that this half voltage in the case of transverse configuration, it gives us an additional freedom of choosing the geometrical parameters L and D, such that the half voltage can be drastically reduced, that is the length of interaction will be more, whereas D will be less. In that case, you get a much less half voltage to switch the modulator. We will continue this discussion for other crystals. Thank you very much.